Welcome to the lecture on foldover design. So far, in last few lectures, we have completed, rather we can say we have discussed 2 to the power k minus p fractional factorial design. Fractional factorial design. Okay. So, what you have seen that in the very basic lecture, we have given you 2 to the power 3 minus 1 fractional factorial design, and where the defining relation was I equal to ABC, and we have taken that I equal to in fact plus minus ABC, and the first fraction is I equal to ABC and second fraction is I equal to minus ABC, and we have discussed the concept called sequential experimentation. Sequential experimentation. Okay. So, this sequential experimentation can be done or is done depending on the purposes that you want to fulfill. So, in more general way, this can be expressed as, or this can be achieved by foldover design. Foldover design. So, what are the important issues in foldover design? Let us see the slide first, and let us start with an example. Suppose you are interested in a resolution 3 design, and the case for demonstration is 2 to the power 7 minus 4 resolution 3 design. If I say 2 to the power 7 minus 4 resolution 3 design, 2 to the power 7 minus 4 resolution 3 design, 2 to the power 7 minus 4 resolution 3 design, and here you see that what is the number of generators P equal to 4. What is the number of factors K equal to 7. What is the number of runs N equal to 2 to the power 3, 7 minus 4 equal to 2 to the power 3 equal to 8. This is a case where K equal to N minus 1. So, this type of design is known as, also called saturated design. Saturated design. So, how do you construct this design? First, it should be a basic design will be 2 to the power 3. So, 1, 2, 3, 4, 5, 6, 7, 8, minus plus minus plus minus plus minus plus 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 minus minus plus plus minus 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 plus 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 plus, and then remaining how many factors are there? So, D will be one factor. So, there will be 7 factors A, B, C, D, E, A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7. Okay. So, you how many parameters you require to estimate here? 7, accepting that one, the mean value, because A parameters usually in this case you have found out, in if it is a to the power 3 design, we estimate A, B, C, AC, BC, ABC. So, A fine, B fine, C fine. Now, this can be AB can be I can say that AB can be confounded with D, AC can be confounded with E, BC can be confounded with F, ABC can be confounded with G. So, that means this equal to AB, this equal to E equal to AC, F equal to BC and G equal to ABC. So, this is your design now. So, 2 to the power 4 minus design. Now, you know how to get the signs for D, B, C, all those things. So, multiplying A, B, all this is what is the construction. Then, if you do the experimentation, what will happen? You will get some y value, y total value. So, now what will be this, what will be this, all those things. Suppose if you fill up all the plus minus here, you will get this structure. You see A B plus minus minus plus plus like this. So, the run, first run where D E F positive, so you are writing that is D E F. Second run A F G. So, that means these are the treatment combinations. Okay. And on other words also, this will denote the total of responses. That is what we have seen in the first lecture on this issue. Okay. So, it's obviously a resolution 3 design, because if you see, find out the defining relation D equal to ABD, AB means ABD is 1, from E you are getting ACE, from AF you are getting BCF, from G you are getting ABCG, plus if you multiplied this ABD and ACE, if you multiplied, A will cancel out BCDE. So, you multiplied these two. So, B will be cancelled out, then ACDF multiplied this ABD and AB will cancel out, CDG. So, similarly multiplied these two, multiplied these two, you will be getting few more. Okay. So, fine. So, you will be having different generators. Now, we all know that to P plus 2 to the power P minus 1 number of defining relations you will be getting. Okay. Now, using this design, if you run the experiment and what results you get from estimation of main effects point of view, considering the interaction effects are higher order interaction effects, means third and higher order interactions are negligible. So, what will be the Elias structure? So, your Elias structure will be, suppose if we neglect the third and higher order interactions, then you will see that your Elias structure will be, A will be aliased with BD, CE and FG, B will be aliased with B, AD, CF, EG, C like this. So, this is your Elias structure. And how you get the Elias structure, all of you know, you just multiply the defining relation by the particular factor. If you multiplied A with ABD, then you will be getting BD, A with ACE, you will be getting CE, A with BCF, you will be getting CF, A equal to ABCG, you will be getting ABCG means you will be getting I equal to A, the BCG, that is not the third order, you do not require. So, this is what is the Elias structure you are getting. So, all the main effects are aliased with second order interaction effects, cannot estimate uniquely. So, under such situation, what you require? You require sequential experimentation if you want to uniquely estimate the main effects or some of the interaction effects. So, this sequential experimentation is possible by switching over the sign of the basic designs. For example, if here A is minus plus, this is the case. So, if you just switch over the sign but reverse the sign, either maybe the one effect, one factor, or maybe all the factors or maybe combination of factors. Once you reverse the sign from the first fraction, then what will happen? You will have a you will get another set of experimental data, and the combining the two you will be able to de-alias some of the effects. Primarily we are interested to de-alias the main effects and second order interaction effects, because third and higher order effects we usually consider they may be negligible considering the sparsity of effect principle, but many a times third order and higher order may be important, and in that case the switching of the sign will be accordingly done. Okay. So, this kind of design, when you do one fraction of experiment, then when you go for the next fraction which is required. So, depending on the purpose, you switch over the sign of one or more factors, and then this kind of design is known as fold over design. So, basically you are folding over to another side. So, the two extreme of fold over design is single factor fold over and full fold over. Okay. So, let us see one interesting example here. This example we have discussed earlier also, to the power 7 minus 3 we have discussed. Okay. This we have not discussed. We have discussed resolution 4 1. Here it is, the this design is to the power 7 minus 4 resolution 3 design. This is what I think the okay to the power same thing, same design. So, here what happened, when you use the first fraction where a, b, c, d like this, and correspondingly confounding other main effects with some interaction effects, and you are generating the plus sign algebraics, that sign conversion table, or I can say design matrix. Okay. Now, here what happened, suppose you do one thing, you do the sign reversal for d, sign reversal for d. If you do the sign reversal for d, so plus minus minus plus plus minus minus like this will be reversed to minus plus plus minus minus like this. Then what happened, your earlier you see what was there, here you have taken d equal to a b, then what you are doing here, d equal to minus a b. Okay. So, instead of d equal to a b, here it will be minus a b, and all other things remain same. Now, if you use this and if you do the experimentation, so here DEF, that you in the first experimentation you will get this Elias structure. When you go for the second experimentation, you will be getting this Elias structure. You see what is happening here, wherever d is there, that minus n is coming. The first fraction is giving a plus bd plus ce plus fg. Now, bd here it is minus. Similarly, here AD is minus, and here no DG is minus, and here D is plus, all other minus, or if you say minus D, then it is minus D and all other plus. So, if you do minus D, if you make it minus minus D, is D plus, then this is the case. So, that means we are basically talking about a single factor sign reversal case here. So, that is why related to D, the plus is becoming minus, and accordingly this is the Elias structure. So, this is basically single fold over, because you have done the sign reversal of one factor, that is D. Now, from the first fraction the Elias structure is this right hand side. Second fraction, when you go for sign reversal of column D, this is the Elias structure. If you use these two and do little arithmetic operations, what you are getting that for, you see that D is de-aliased. The main effect D is de-aliased, and A, B, C other things are aliased with A is aliased with some other second order interactions, and other main effects are also aliased with some other second order interactions, but some of the second order interactions are not aliased with other second order interactions, may be aliased with higher order, but they are negligible. So, this gives you a better picture. Intentionally you have basically done the sign reversal for only one factor d, and that is why the uniquely you are able to estimate the effect of d. Now, if you do it for the all the factors, what will happen? Giving the two data set, you will be able to de-alias all the main effects. So, that means when you do the sign reversal for one factor and then do the experiment again, you have two sets of experimental data. Using these, you are in a position to find out the effects. Effects in the sense the effect of interest uniquely can be estimated. Okay. So, for then other one is the full foldover design, where you do all sign reversal. So, let us see that the same thing here to the power 7 minus 4 3 design, and here suppose you have done the using the first fraction, then you have done the experiment and you got these are the experimental results. So, if without going for the sequential experimentation, if you use this one, your estimate is like this. So, if you see the Elias structure and the estimated value, that A, B and D, which are basically high value. So, we can say A, B and D are large. So, now using the Occam-Razor principle, we can say A, B and D effects are significant, but this is not the unique interpretation, because there may be the second order interactions also, because A and B significant mean A B interaction may be significant. Similarly, B and D significant mean B D interaction may be significant and A D interaction may be significant. So, then if but as A is aliased with B D, so but just by seeing this value, you can say using Occam-Razor principle that A is significant obviously, but what will happen to B D? You cannot uniquely say that what happened to B D. So, as a result, suppose you go for a full foldover design, means here you see that ABC sign conversion from here minus plus minus plus minus plus like this minus minus minus, all those this ABC, the basic design, the sign conversion taken place, plus minus plus minus plus minus like this. And as a result, you see the D also all cases minus minus A, that means here AB, AC and BC, they are basically sign reversal is taking place, and G, because of ABC, this sign reversal is. Now, if I go to G, it is minus plus minus plus, here what happened plus minus is, it is also sign reversal taken place. So, you have done using first fraction your experiment and this is the result. Now, you have gone for full foldover and then your this is your results. So, from the first fraction what happened? From the first fraction you got this, from the second fraction you got this. Now, if you use this arithmetic, that half within bracket I and plus I dash, that is mean first fraction and the foldover fraction second fraction, then first fraction minus second fraction, what are you getting? You are in a position to find out all the main effects parameter uniquely estimated. In addition, what you are finding out that the second order interactions are basically grouped in a 3, aliased in group of 3, and you see that BD, CE, FG 19, but other values are very less. So, we can say this is what is the significant one, this BD, CE and FG. But if you see the first order interactions, main effects, not first order interactions, main effects only, you say the B is significant, D is significant, but A, C, E, F, G they are not significant. Okay. Now here if you see that only the first fraction results A is 20 and this, so they are using this, you have said or I have said that A is significant, because seeing this value high, A, B and D, these three are significantly high. So I say A is significant. But after doing fold over, when we got the second fraction and de-alias the effect of A, but the effect of A is only 1.48. So that means then where from this 20.63 is coming? See, there is one interaction called BD, and if you see the total data after fold over design, so you see that B effect and D effect are significant. So that means its interaction effect will become significant, because here A plus and other effect like C, E and all other main effects are not significantly large. So if B and D effect is significant, then BD interaction is possibly significant, and here although A is 1.48, so from here 20.63, so BD plus C plus FG is 19.15. Now here what we are trying to say, as C, E, F, G all other effects, main effects are negligible, it is quite likely that C, E and F, G effects also will be less. But as B and D effects are significantly high, it is quite possible that BD significant, BD interaction effect is significant, and as a result here the BD is bold, means we are saying that second order interaction BD is significantly large. So suppose this is just by seeing these values A, B, C, D, E, F, G, and by seeing that what is the value. What I say that you can go for normal probability plot also, all those things. So if you do normal probability plot, how many estimates are there? Suppose from there here you can say that A, B, C, D, E, F, G and B, D also from here you can take, and then if you do normal probability plot, it is quite likely that A, C, E, F, G and this will basically form a straight line, and this B effect, D effect and BD effect, this will be falling apart. Means what I mean to say, even if you do the half normal also, and then if you go for cumulative percent probability and here effect, it is quite likely that A, C it is quite likely that A, C there will be maybe something like this, which is basically C is minus, then A is 1 point, E is 0.13 somewhere here, so minus 1.8 here, 0.183 here, 0.50 another one, that G, then 0.50 somewhere here, and then your 0.13, 0.50, then 1.48 maybe somewhere here, and in this manner if you go, you plot this line, and A, B is 38 point anything somewhere here, D is 29, 29 maybe somewhere here, and BD will be 19 maybe somewhere here, 19. Okay. So BD will be 19, cumulative probability will be this somewhere here. So what I mean to say, if you go for normal probability plot, you will find out that these effects are significantly higher, and as a result they will not follow the your plot. Okay, this is normal probability plot, normal. But if you go for half normal, then the C negative value will become positive, and accordingly you do. Okay. So otherwise you use length method. So, length method we are not discussing, but in the length method is a two-stage method, and you Google it, and actually you do some kind of study with yours. So, this is what is basically fold over design. Now, let me do this one, that what is, I am just giving you the gist or summary fold over design. First is you have fractional factorial design. You have chosen a particular resolution, and your interest is find out some fx. Maybe primary interest will be all the image main effects, then your second order interaction effects. So, rarely may be third and higher order interaction, third or higher order interaction. Depending on the resolution, what will happen ultimately, suppose if you choose resolution 3 design, then your main effects will be aliased with second order interaction effects. After the first fraction, so you conduct experiment using first fraction. So, you get some useful structure. So, like this, and there are some useful values and some other alias structure also you will get. So, by observing this, you will have certain idea, some preliminary idea will be there. Like here we said that A, B and D are significant. But what happened, as A is interacted with B, D also, and B and D is significant. So, it is difficult, for example, like here you see A, let me go back again, here A, B and D, their values are high. Now, and if I see the Elias structure, A is interacted with B D, aliased with B D, C and F G. C and F G fine, because C, F G, their main effects are not large, but B D both main effects are large. So, their interaction effect may be large. So, that is the interesting structure. So, A, if I say, that means primarily A plus B D, that is the issue. And again, as B, this one is large and D is also large. So, if we assume that B and D are significant, and then again B case, you see that B plus AD, as A and D, this one with alias is large, this is also large, this may be large. So, then the question is whether B is large or AD is large. And third one is also, if you go for D, in the D case, that D plus AB is there. So, as A and B, this with alias is large, we do not know whether it is A large, B large or AB interaction is also large. So, that is what is interaction structure you are getting. If you get this kind of structure, then what you require? You require to go for sequential experimentation. And in sequential experimentation, you can go for single fold over or full fold over or combination. Means single means you will reverse only one factor, sign reversion. Full means all, and combination means some will be sign reversed, not one, not full, in between. Okay. So, then you will get another fraction, and when you have another fraction, you see the results. Suppose here you see the other fraction, A value minus, B positive and D positive. So, here also see A positive, B positive, D positive, but their large value, the large value part is remains same here, but B and D they are positive, but A sign reversal has taken place here. So, this indicates that the interesting, these two indicates that okay, there is a problem with A, and when you use these two results, combine the two data set, and then finally de-alias the factors, then what you are getting? You see, you are getting A effect is negligible, B and D effect is significantly large, and so then from here you are getting BD effect with some alias is 19.15. So, BD effect is also large. That is what is the conclusion. So, that is what why this foldover design is important, and I hope that you are in a position to understand that what is foldover design and why foldover design is used, and how foldover design will help you in de-aliasing the some of the main and second order interaction effects, and also how to interpret the effects, whether they are significant or not, and obviously you will be heavily using that probability plotting for effects and to get the value, whether significant or insignificant or not. Okay. I think this is enough for foldover design, and please remember I am following the book of Montgomery, and you all must purchase the book and read the chapters, corresponding chapters, and you will definitely understand this, and I find this a wonderful book. Thank you very much.